Hi, I'm Fernando Pereira from UFMG, and today we shall talk about Twelf. This is a meta-theorem prover, meaning that it checks the proofs that we write. Twelf was developed in Carnegie Mellon by Frank Fanning and Karsten Schumann. Most of the material in this class has been taken from the Twelf tutorial, which is freely available in the Carnegie Mellon website. There are other meta-theorem provers. Perhaps Koch would be the most well-known. I chose Twelf because it's fairly readable. Proofs in Twelf look pretty much like proofs that we write by hand, once we get used to the syntax. To show how it works, we shall start looking into the definition of natural numbers. We can define numbers following Peano's axioms. So, first of all, 0 is a number. That's the base case of our definition. Second, if n is a number, then suc of n is a number as well. These two definitions are among the 10 axioms of Peano to define arithmetics. The first definition is Peano's first axiom. The second is Peano's sixth axiom. So, how can we define even numbers? Would you like to think about this question? Later on, we will use these definitions to demonstrate how we can prove theorems in Twelf. To define even numbers, we follow similar principles. First, 0 is an even number. By the way, whenever I say number, I really mean a natural number. And if n is an even number, then suc of n is also an even number. And how could we define addition over the naturals? We define addition using two predicates. First, 0 plus n is n. Second, if any1 plus any2 is any3, right here, then suc of any1 plus any2 is suc of any3. And here we have our definitions in Twelf. Twelf is based on a theory called dependent type theory. The real meaning of dependent types is not very important right now. But every predicate in Twelf defines a type. So net, the term for natural numbers, is a type. Z, the term for 0, is a type because it's net. And S, the term for successor, is a type constructor. It receives a type, that is a number n, and produces another type, that is the successor of n. Some definitions are axioms because they require no premises. We are saying, for instance, that z is always a number, or we are saying that z plus n2 is always n2. Other definitions are lemmas. Given two premises, we can conclude a fact, like if n is even, then the successor of n is also even. To check if the program is correct, you can load and validate it using Twelf. The commands are given on the right. I'm saving these definitions into a file called number.elf, and then I load a file called sources.cfg. CFG is the common extension for SML configuration files. Twelf is implemented in SML New Jersey, by the way. If you get an OK after you load the file, then that means that your definitions are sound. So before we move on, can you see how your definitions on the left side correspond to the Twelf script on the right side? Stop the video and try to find a correspondence between them. We can even program using Twelf. It has a REPL, and we can issue queries like we do in Prolog, just like using the command top. Then you can have queries like those in light yellow on the right. This is a query, for instance. Another query, and in this case n must be this term here, so that this query will be true. But Twelf really shines when we need to write theorems and prove them. For instance, let's try to prove the following theorem. If any1 and any2 are even numbers, and any1 plus any2 is any3, then any3 is an even number. How can you prove that? As a starting point, we have 3 facts from the premises in the theorem. So let's try to write this proof by hand, without any support of a mechanical theorem prover. First, any1 is even. Then any2 is even, and any1 plus any2 is any3. Those are the facts that we start with. Let's consider the first predicate. Any1 is even. In how many ways can we have that this definition holds? Basically, either we have that any1 is even because it's 0, or any1 is the doubly successor of an even number. In the second case, let's call this even number any1 prime. So how can we move on from these observations towards the final proof? In the first case, we have that any1 is 0, but any1 plus any2 is any2 because any1 is 0. And as a premise, we already know that any2 is even. So we're done. If any1 is suc of any1 prime and even any1 prime is true, then we know that suc of any1 prime plus any2 is suc of any3 prime. From this observation, we arrive at the fact that any1 prime plus any2 is any3 prime. Applying induction on this fact, we get that any3 prime is even. But then any3 is suc of any3 prime, which must be even due to the inductive case of the rule is even. The question now is how we write this proof in Twelf. I will show it. But be aware, the program will look weird at first, but then you will get used to its notation after looking at it for a while. Here's the proof in Twelf. There are many things to digest. Let's analyze the script. First, in blue, that's how we state the theorem. It reads pretty much like in English. If any1 is even, right here, and any2 is even, and any1 plus any2 is any3, then any3 is even. The second line in red is the mode of the theorem. Basically, we are saying that given the 3 first facts, the fourth must be true. So these 3 first facts are inputs. You have that with the plus sign. And the fourth fact is an output, indicated by the minus sign. Next comes the proofs themselves. The first proof is called SEZ. That's the name of the proof. A proof is basically a way to state the theorem. So we start invoking the sum-evens theorem. So sum-evens is the name of the theorem. But we need to fill the 3 facts and derive the fourth. The first fact stating that any1 is even is the rule even z here. It has been defined here. The second, I call it even any2. It's an open fact. Open facts start with uppercase letters. It can be any way to show that any2 is even, so we don't care. The third fact is plus z, the sum where the first number is 0, so here's plus z. Now, how do we conclude the fourth fact? That's simply even any2, our open fact. For we just need to show that any2 is even, as any2 and any3 are the same number, in this case. So we are given facts and we need to derive the conclusion of the theorem. A proof must consider every possible way to write this fact. In this example, there are 2 ways to write the first fact. And here comes the second part of the proof then. That's a bit more complicated. Before we move on, perhaps you could stop the video and try to read the proof? Maybe that's asking for too much, but I guess you can start understanding a little bit what's going on. This proof concerns the case when we know that any1 is even via rule evenness. The proof has a dependence, something that we assume to be true. In this case, any1 must be the double successor of an even number. So our dependence uses this fact, the even number. I'm going to show a drawing, and the proof will be clearer. So let's look into the proof. Everything in a proof is an inference rule. For instance, the first fact consists of two rules, even s and some premise of even s, right here, which I've called even any1 prime. The third fact is a derivation with three inference rules, here. And here are the names of those rules. The two first rules are plus s and plus s. The third rule is the premise, which I've called plus. So, because we have all these rules, we have more facts that are true. Everything in the premises we can assume to be true. In particular, we have three facts that are true. They are called even any1 prime, even any2, and plus. And we can plug them to derive something by induction. So we are plugging these facts into the theorem itself. Then we can conclude that any3 prime is even. The inductive hypothesis gives us this new fact, even any3 prime. That says that any3 prime is even. So here's how that looks like in Twelf. We take the known facts and build a new fact through induction. So these three facts, they are known, and here's the fact that we derive out of induction. And then we derive our goal using this new known fact. So if we apply even s using even any3 prime as a premise, then we prove that suc of any3 prime is even. Notice that to prove that any3 prime was even, we had to apply the theorem again on smaller derivations. I say smaller, meaning that these rules are up in the derivation tree. So you can see the rules being applied inductively on the left. The total clause at the end of the script explains which part of it we are using as the inductive case. So the first fact is used, meaning that in our proofs, either this first fact is reduced or it consists of an unreducible rule, a rule without any premise. And with this first example, we conclude our introduction to Twelf. In the next class, we shall see a few more examples of proofs and definitions. Till there, you feel free to write me with questions or comments. Thank you.